Right, so today we don't have any real new lecture topic, but want to answer whatever questions you guys have on any questions you have on starting things up. Hopefully some of you already made some of your data, because you got to get, cones and not cones. So that's, pretty much the first place to start. We also have to build the histogram of oriented gradient features and the color features. So what problems you guys had so far? Anything?
Your support vector machine lecture online doesn't have any sound, and it doesn't work at all.
Really?
Yeah. So I was going to ask you, at the end of that lecture, you said you changed something and it made it a lot better. I was wondering what you changed.
Changed what to make it a lot better?
You changed the parameter on your SVM.
Right. There was, in the SVM, I used, let me pull up because I have an SVM example, right? What I have in here is the better one. Where is, oh maybe, yeah, here. So here I have combined the making an instance of the SVM and fitting it in one line, where before I've done it in two lines. But this is the SVM, which is the module, sklearn module SVM, and it uses SVC, which is a support vector classifier. That's the better one to use. There's also a linear SVC. Okay? And so the linear SVC doesn't use the kernel functions. It just has a straight up linear hyperplane in your feature space that you give it. So if you're using this one here, you're already in the better one. So the lecture for the SVMs didn't have sound. Did the next ones?
I didn't get that far, but it wasn't even that it just didn't have sound. Like the first screen popped up and then it just stayed there for 50 minutes. Yeah, it stayed right there the whole time.
Okay. Well, that's a shame. So then let's see, what was the next one? Was non-maximum suppression came after that? So this has audio. Seems to be working okay. Let's see, what was the last one we just did?
The perspective transfer.
Yes. Am I not talking? See, this one did the same thing. That's really weird. That's a shame. Snagit just sometimes doesn't seem, I don't know if I'm clicking somewhere in the wrong way. Like, I wonder if I accidentally clicked on something in the, maybe I did that. Maybe I hit, I clicked on the system tray and paused it. Maybe I accidentally did that rather than pulling. Yeah, so I think if I click here or if I click there, it pauses it. It must have been what I did in one of those cases. Interesting. Well, that stinks. I need to be smarter on how to use that thing. All right. Sorry about that. Okay, so we got the SVM. We want to use the one that's in here, not linear SVC. Okay. Other issues that anyone's having?
I'm at the point where you got to do the reprocessing StandardScaler part.
Okay, that's true. I never talked about that. That's a good point. And what's really interesting? I wonder, I'm glad you brought that up. I did mean to talk about that. So one of the things in machine learning that is a pretty standard approach is to normalize your input data. And the idea is that if you have, I guess in a support vector machine, maybe it doesn't, I'm trying to come to a good example, but essentially if you have some features that have values that range between 0 and 1, and you have other features that range between 0 and 10,000, okay, there can be scaling issues. Now with a support vector machine, I mean, if you're doing just a linear one, just a linear support vector machine, you've got this plane, and that plane is just going to have different slopes in different directions to account for that possible difference. You know, you might have a slope of 0.1 in one direction and a slope of 20 in another direction. But if you're using kernels, that might end up making things tricky if you're doing like x squares, for example, and one thing, you know, one dimension is getting x squared and the other dimension is getting x squared, and there's much larger values in one of the features, that may end up as an issue. Okay, it will become more important when we talk about gradient descent and neural networks, where you're looking at how much you're decreasing an error, and that error can very much depend on, you know, how big things are. So it's a very typical thing to do to normalize data. Okay, so for example, if you have something like okay, so if this is our data, actually maybe I'll make that NumPy. Make that a NumPy array. Okay, so if we have an array, what we would like to do is to make this have a zero mean and a unit standard deviation. Okay, so we would take x and we would subtract. We would say, let's make x subtract from x the mean of x. Doesn't like, well, maybe I'll do this. Maybe it won't do element. Maybe it doesn't do element. Yeah, it doesn't do element-wise subtraction. Isn't that interesting? The minus equals doesn't seem to be element-wise subtraction. So now you can see the x's all have, you know, if I take x dot mean, or numpy dot mean of x, okay, it has an average of 0 value. So, you know, if there was a big shift in this, if like the values were all like 6 million, 6 million and 1, 6 million and 5, you know, shifting them to zeros makes it not have such a high value. Okay? Now the other thing that you can have is you can have a very large spread of the values. Now these values don't have an exceptionally large spread, but they have a standard deviation of 2.6. Now other values might have a much bigger standard deviation, like some values might be right around 1, some values might be at 100, you know, and so you might have a very large spread of them. So not only might we want to shift them, but we might want to scale them so that they don't vary so much from each other. And so then we can also take x is equal to x divided by the standard deviation, the numpy dot standard deviation of x. Okay, and so now you can see the x values, and if I do x dot mean, if I do numpy mean of x, I get a 0 standard deviation, and if I do numpy standard deviation of x, I get it has a 1 standard deviation. So this is a very typical thing to do, is to make things be work that way. And so what is a very common thing is you take each feature and you normalize each feature to have a 0 mean and a unit standard deviation. So I've already showed you how you can do this manually, and so you could loop through each one of your features and take that array of all of your feature values in your training data and, you know, take the mean and take the standard deviation and do this way. There is the StandardScaler in sklearn they have this guy. Let's see, standard or scalar. Let's see, where do I talk about the scalar?
It's just right there.
Here.
In the classifier training.
There we go. Now, did I make that a rubric requirement? I did. Okay. All right. So let's see. And then let's do this. NumPy array, make that a NumPy array, and then the standard scalar. Let's do this. I'm pretty sure you just pass it a feature matrix. Let me double check that.
Is your test image going to be a 1280 by 960 like the training image?
Yes.
Okay.
Yes, it'll be the same resolution. Isn't that strange? Here we go. Right. Okay, right, you do standard. Okay, so we'll make, say, our scalar is this, and then, you know what, let's make two features here. Let's column stack two things. Let's column stack that and another feature. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then scalar dot fit x, and then it's not predict. What is it? Transform.
Yeah, it's
Transform.
transform.
Scalar dot transform.
You can do a fit transform, but it doesn't save the scalar value to use for later data.
Right, and that's something you definitely want to keep. Right. So if we do this, then let's see, print x, print, no, x scaled, print x numpy dot mean x scaled numpy dot standard deviation x scaled. So no, you know what? Put in here. Example scalar. Okay. Doesn't like this line. Why does it not like that line? It doesn't. Oh, this line probably is improperly done. Yes, that's missing the parenthesis. So it wasn't line 10. It was line 9. We need to import numpy. Import numpy as np. So let's try that. So let's see what happens. sklearn has no attribute preprocessing. let's do it this way. From scalar import standard scalar. Then I guess we can do it like this, right? Is that the way they did that? I always am unsure how they do. Yeah, right. Yeah. Then we can just call standard scaler by its name without any periods. Right, let's try that. Yeah, we got something. Okay. That's true. So let's do this. We want to look at each. So the NumPy mean took the mean of all of the values. We want to do each. So overall, they have an average of 0 and a standard deviation of 1. But we want to show that each column actually has that. So we'll do, let's take all the rows, the 0th column, all the rows, the 0th column, and we'll show that it's true for both the 0th column and the first column have an average of, right. So now the 0th column has an average of 0, standard deviation of 1. Second column at average 0, standard deviation of 1. So these values all have an average of 0, standard deviation of 1. These values all have an average of 0, standard deviation of 1. And they match the original x values, that these guys here are built from these original ones. Okay, so it's a nice way to not have to loop through. If you have lots of features, you don't have to loop through them. But what's even nicer, so if you were going to do your training here, you would calculate all your features. You get a feature matrix, and again, like all of these, every row is a new sample, and every column is a new feature. So in this example, I have 8. There are 8 there, right? Is it 8 or 9? There are 8 samples that each have 2 features. Okay? So again, that's the standard way of representing our feature matrix. Every row is a sample, every column is a feature. And so you'll calculate your features, you'll get your feature matrix. In this case, you're going to have however many rows you have there's a total number of images, both cones and non-cones. So maybe you have 40 or 50 rows in your feature vector, and then you're going to have a column for each of your hog features and each of your color histogram features. So that's going to be very long, very wide. So I don't know, that maybe in the thousands. Okay, so you've got thousands of columns. You have about 40 or 50 rows. Okay, and then you will pass that feature matrix 2D NumPy array to fit your scalar, with. And then the result of that is going to be the same size matrix or same size 2D array that you had in the original one, but they're going to be the scaled feature values. Okay? Then those are the feature values you're going to send to the fit on the SVC. Okay? The labels, they're going to be either 0s or 1s. I mean, if you wanted to be really particular, you would change those to be, positive 0.62 and negative 0.62, so that they would be a 0 mean and a unit standard deviation. Okay, that's not really necessary. The whole point of here isn't to have exactly 0 mean and 1 standard deviation, but just to have them be reasonable values, and if you have multiple features, for them to have similarly scaled reasonable values. So if you have a single output and it's either 0 or 1, you really don't have to do anything about that. So you can pass your regular labels, but you pass the scaled input. Okay? And so in that training process, nothing else happens differently. In the prediction process, nothing happens differently. You'll pass your those scaled feature values, and they'll tell you the results. And so in order to evaluate how well you're doing on the training set, you will do nothing different other than just always use the scaled values. Okay? Now what you will need to do differently is when you're going to test on new data. Say you've got this new training image, or maybe you've gotten your own image off of the internet, or you've taken a new image out there in Q118 and you want to test on that one. Okay, you're going to take that image. You're going to calculate all of your features with that. This 50 by 3000 feature vector for the new things. Okay, and then you're going to transform those, and that's why you need the scaler. You need to keep the scaler. That's the instance of the scalar object. And so you'll take the feature values of your test images, of your test pieces, or even in your sliding window search. When you're going through your sliding window search, you're going to get that list of features, and you're going to need to scale those features into that scaled space before you predict them with the SVC. Okay. Now, I do want you to practice doing this. It does say to do it in the rubric. I can't be sure, but I think I remember that oddly I got not as good results when I did the scaler.
I think I got better.
You got better? Okay, well that's good, because you're supposed to get better. Okay, and I can't swear, because I've been doing some of this stuff for the next project lately, and I'm pretty sure I was actually getting worse values when I was scaling it. But you should see better.
One problem I did run into though is, so whenever I did I have the 90 pictures by thousands of different features.
Right.
When I put that into the standard scaler, it worked fine. And then when I was doing my sliding window search and I tried to put just one column into it, it says, no, I'm expecting 90 of these. Why are you only passing me one?
Okay. I'm not sure why it said 90, because that was the number of rows, right?
That was the number of pictures that I was using.
Right. What can happen is that if you pass a 1D array, and it's expecting a 2D array, it can get confused over which things is the rows and which is the columns. So let's test that. Let me see if I can recreate that problem. Let's create another 1Y, and let's make it have, well, let's do it first. Let's just make it a NumPy array. I'll just change some of the numbers in here, just for fun. Okay, and let us see what happens when we do a fit on that. Let's do scalar. I'll do print scalar dot transform. So that's kind of like the k-means cluster. They don't predict, they transform to a new space. Interesting. And then we'll pass a y. Let's see what we get when we do this. Okay. It expected a 2D array, it got a 1D array instead. That's not the error you got?
No.
Okay.
And I was saying it was because I had 90 image, but I think I did mine, all the features were in up and there were 90 different.
See, that's wrong.
Okay, so I need to
you need to transpose that.
Yeah.
So what it did is it normalized across that all the images got their feature number one. It got normalized across images rather than across features. Okay. So it normalized in a different way. But that's interesting that you say you still got better results when you did it that way.
Well, it wouldn't work, and so what I did is I just did it on my first image, and then I just used that same thing for everything.
Yeah.
And I got decent results.
Okay.
From it, but.
So that's the one problem that you have. Okay, is that you need to get that transpose, and that's why I would have expected it to say I was expecting something 3,000 long. Mm-hmm. That's what I would have expected it to give you an error with. Okay. Now this is a slightly different thing. And I've seen this before where they tell you to do the reshape. Let me see what happens with that. Num y dot reshape -1 try the other way too. PPQ is equal to negative 1, 1. And let's do print y, do print yp, and we'll do print yq. Let's see, what do we get? Okay, so here is the original y. This turns it into having one row, and this turns it into having one column. Okay, and so the reshape turns it from one dimension into two dimensions. And basically the -1 is there to say which dimension you're trying to create. The one is I want to keep it in that axis. So that first axis I want to keep, and then the -1 is where I want it to move into. So that's one way. Another way is that you can say I want y to be equal to a well, let's do another thing. We'll do w. W is equal to numpy zeros that I want it to have one row and 8 columns. And then I can say I want w, the 0th row, all the columns of w to equal y. And then I think that will work as well. Print w here. Let's see what we got. So yeah, that's y. This is w, where I explicitly created it to have 2 dimensions, to be a 2D array. You know, being numpy np zeros 1 comma 8 is different from 8 comma nothing, because if you do 8 comma nothing, then it's one dimensional. Okay, and so here I've gotten w by making it a 2D array, or I can do reshape on the original one to either make it a row vector or a column vector. And so I should then be able to pass either yp or w. So if I pass yp, that didn't like it. Operands could not be broadcast together with shapes 1.8. Oh, the mean. Some of the mean stuff didn't. Where is that? Oh, it is in here. 1.8, 2, and 1.8. Isn't that in? Oh. So there's something about it's still wanting to have 2. Oh, right. Yes. Okay, so I did the wrong one. It's not going to work on yp, because yp has 1 data point and 8 features. But our stuff has, my original thing had 8 data points and 2 features, so I sent the wrong one. It should be yq that should work. Still didn't. What about if we do 8 comma 1 for w, and we pass it to be like this, and try w. It's not going to like that either, probably. It did like that. Isn't that interesting? No, it didn't like that. What is going on here? Boy, how's it caught in the middle of something? Okay. Alright. Non-broadcastable output on. Right, of course. I'm really stupid. Okay, so in this example, there are 2 features, and I'm trying to give it 8 features. One, I tried to give it, well, W. Let's look at W. W is this. This is W. That is 8 data points and 1 feature. And the original thing had 8 data points and 2 features. So this needs to be 2. Y needs to have only 2 things in it. And I want there to be 2 columns. Now that might work. Yes. Okay. So what happened now, let's go ahead and take these guys out. Okay, so now my W has 1 data point and it has 2 values. And so this, with the double brackets, the double bracket, these brackets show the 2D array, and then each side, everything inside the first brackets gives you a row. Okay, and so this is 1 row, 2 columns. And let me see, let's just straight up pass up Y, because Y is a 1D array. Let's try to pass Y. Let's see if it will take Y. It does not. So it doesn't like Y. I've passed it 2 things, but it wants to be sure that those 2 things are in a 2D array. It expected it to be 2D. And then, let's see, so YP, let's see which of YP's is the right direction we want. That's Y, this is W, this is YP. YP is okay. YQ is not what we want. So it should work with YP as well. And it does. Okay, so I need to send to that scalar transform, I need to send it a 2D array. I can't send it a 1D array, which you're probably going to have a 1D array for that one window that you want to analyze. I wonder if it would be any faster if you had your window and you got the feature values for the window and you kept concatenating them together into a feature matrix, and then you did the standard scalar transform on the matrix of them, and then you classified the matrix of them, but then you'd have to go back and fill in it would be hard to make the heat map and all that. So it would be kind of painful to do all of them in one batch. It'd be really easier to do it in one. I think most of the time is not in making the transform and the predict. Most of the time I think is in the image processing of getting the hog feature. So it probably wouldn't even save you much time. But you'd want to do it one at a time. So probably you're going to have a feature vector that is just a 1D array, and you're either going to have to reshape it or place it inside something that you've purposely created as a 2D array. So definitely do the standard scalar and try it, but it might be worth testing and seeing whether you get similar results. Well, you know what? I think I got worse results. I was using the linear SVC. If I didn't use the linear SVC, maybe it would be better.
I just got worse results doing it because before I did the standard scalar on just the very first image, and then I just applied that standard scalar to every single image that I did.
Right.
And I got better results than when I just changed it and did all of them at once.
For the scalar.
For the scalar, and then was just sending singles. I can show you this.
Yeah.
This one was when I just changed it, and this one was beforehand.
And you're not even really needing the heat map so much when you're using your heat map isn't really getting rid of anything, is it?
No. Well, that's another thing I was going to ask you. Is this heat map down here? These 3 are cones, but they're so close together that they're counting it as one. And if I would have to kick that out because it's too big.
Right. Right.
But I did use like 195 images versus.
But I got similar results that when I originally wrote the procedure, I was using the linear SVC, which was not as good.
Yeah.
And I had a lot of false positives because the classifier wasn't as good.
Yeah.
And so I felt there was a need for the heat map then. And so, I needed to have the heat map for that, but when I switched it to be a regular SVC, I got similar results like you where there weren't really any false negatives anymore.
Yeah.
So,
oh, and I have a different testing image if anyone wants.
okay, you've already taken another one.
That's the middle.
Good. So I guess all the other stuff, I mean, using the labels and doing the bounding boxes, it's really that heat map piece is the only one that may or may not be useful. So.
But it is useful for most of them. It's just like, and I've got 10 outside of the heat map.
But have you filtered away anything out of the heat? Have you gotten rid of anything that had small heat map values?
I got rid of anything that was just a 1.
Oh, okay.
Yeah.
So but do you have an image that shows all of them?
No, I can get it.
Okay. That would be interesting for me to see. So then the heat map may actually be useful for you. That you're getting rid of things that just have 1.
Yeah.
Okay. Okay, good. That's good that you're getting it. It's still somewhat useful. So then I need to, let me go ahead and upload this StandardScaler example to D2L so you have that.
Yeah, that one was a little weird to try to figure out on your own.
Yeah, I had forgotten about it, and it's a perfect topic for today, so I'm glad you asked me about it. Example scaler. So that can be useful. Alright. Did you get that image?
It's coming. It takes it like exactly 55 seconds to get to the sliding window search. Alright, so this one is before anything is taken away.
Okay, so it does take away gets rid of some useful stuff that you don't want. That are, false positives. Okay, good. I'm glad to see that then.
And like I said, I still got 10 cones out there, but I mean,
Yeah.
this would make it 13, which it's identifying them correctly.
Right, but it's too big. It's too close. And so, I think the best thing for you to do is just throw it away, because you've already, and I knew that was going to be a situation, so that's why I didn't ask you to be able to detect all of them or nearly all of them, because how many are there? There's 18 or something? Yeah. So I'm asking you only to get basically half of them, because I know that can happen. And when I took the original image, there were a lot more and they were a lot closer together. And I mean, that's a whole nother issue of being able to separate separate them.
Yeah.
And I didn't want to go there for this project. Cool. I'm ambitious, but I'm not that ambitious. So yeah, just drop that one, because if you can do that well in that image, you're probably still going to get at least 5 in the test image, even if it glops some of them together.
And also, you said that you want us to save all the images and do like a glob.glob to bring them all in. What if I just saved all the images as a list with, it's got just the 3 pixel values just in a list?
Well, I just want to be able to see your pictures.
Cool.
So if there's a folder that has all of your pictures in it, and I can,
pickle file, not a folder.
I want the images to be there so I can look at your images.
can I just submit an extra thing that has a for loop that runs through the whole pickle file that'll show you all the images?
Yes, or just, oh, you say rather than saving them.
Rather than saving them individually?
Okay. Yeah, I suppose.
Okay.
Yeah, I just want to be able to see
I
them.
wasn't reading that part whenever I went through, so I just saved all the images as, all right, well, part 0 of list 1
Right.
contains a 3-dimensional array of all the pixel values of the image that I used.
Oh, well, that's the same thing.
Okay.
I mean, that is the image.
All right.
Then all you have to do is I am right on that.
I am right? Okay.
Yeah. A plot, it should be plot.I am right. Should be able to, yeah. Because you've got a 3, it's the RGB layers. It's not, it's 100 by 50 with 3 layers. Yeah, you just do an I am right on that.
Okay.
And you say what file type you want a JPEG or PNG or whatever.
Okay, cool.
Yeah, I just want to be able to browse through and look at what your cones and non-cones look like.
I do have 195 images, though. Is that going to be too much to submit?
Shouldn't be.
Okay.
Because they're not big resolution.
No, there's 60 by 70.
Yeah.
Which was another weird thing in trying, because the row and columns when you're dealing with images is all like
Yes.
swap.
Yes, that is so
I used
annoying.
60 and 70, so I was having to go through and figure out, all right, does it need to be 70-60 this time or 60-70?
I know. I know, that is very annoying. Yeah. Most of the image stuff I find is mostly XY, but it's only when you're actually indexing things when it ends up being row and column.
Yeah.
Definitely Matplotlib, but almost all the Matplotlib stuff is XY. And even a lot of the OpenCV is too. All right, how about the rest of you? Any others? You guys haven't gotten far enough to have problems yet?
I'll let you know on Monday.
Yeah, okay. Yeah, I have the weekend to look over some stuff and work out, see where you can get. Got a question, Hannah?
Oh yeah, probably an obvious question about the data. Would it be better to say when we're getting pictures of the cones, even for the cones that are farther away, should we just keep it, say, the window the same size and get, say, the blank space around it, around the cone, or try to fit the pictures as close to the cone as possible?
So that is a good question. So she's asking, if you've got the cone that's far away that's small, should she keep the same size so the cone is small in that 60 by 70 if it's the same size, or do you reshape it so that it fits the 650 by 60? I think probably if you're going to search at multiple scales in the image, I think resizing it is good. So if you're going to go through your image and look at multiple check at multiple scales, then the smaller ones will end up filling the whole window. In this problem, you probably are not going to be able to do multiple scales and still get under a minute of being able to go through the image. Okay, like Justin's just shaking his head. There's no way you're going to.
Like, I kind of want to put my code on your computer and make sure it runs in under 60 seconds.
I have that machine too.
Okay.
And I think it's slower than mine, but I'm not sure.
Even better.
But if it's a minute and 10 seconds or something, I'm not gonna. I just don't want it to take forever.
It shows how long it took on my
computer. Right. That's good. That's good. So if you're going to be doing a single scale at the size of the largest ones, then it's probably better for you to center, get it in the center and have it be small in the background. Because then as your window goes across there, it's going to hit something that looks like what you've trained on. So in this project, it's probably better to leave it centered and small in the background, but if you were doing something more bigger and a better one where you're looking at multiple scales, you'd probably want to resize it. Okay. But that's a good question, Hannah. That's not a dumb question.
I used ones that were smaller in the back and then bigger in the front.
And you left them small. You left them small in your training image. Yeah. That's my recommendation.
And when I went across on the sliding window, I used the exact same box size that I used for.
So you skipped a box. You didn't have any of your boxes overlapping?
No,
Or-
I have the boxes overlap. I just used the same 60 by 70.
Oh, right, yes.
Go.
Right. Because the test image has the same resolution as the original image and is about the same distance from the field. Yeah. Right. No, I did the same thing where my window was the same size as the original images that I trained on.
Yeah.
Yep.
Also, since I'm using OpenCV and a lot of the making data and the images coming out are in BGR, would that pose a problem then? Or should I try to convert the images after they come out so
Right.
those are actually yellow?
So OpenCV is BGR, Matplotlib is RGB. As long as you load the image in the same way all the time, you should be okay. So what my recommendation is that this is what I do at least. I load the images with Matplotlib. I display the images with Matplotlib so they don't look funny. And then if you use OpenCV things in the middle, you'll be fine. Because it will just think red is blue, red is blue and blue is red, but it's symmetric. The things they do on them are symmetric, so you won't get any problems there. So you don't have to convert it to BGR before you send it to an OpenCV thing, unless it's a display function.
Yeah, because my data's coming back with cyan cones.
Right. You should be okay if you load in with Matplotlib and display with Matplotlib and do OpenCV stuff in the middle. All right. So hopefully that all